All right, Chapter 5, gases. So we are going to really talk about the physical theory side of how gases work and how they're going to affect refrigerant and in the heat transfer capability. All right, so we're really talking about the basic fundamentals of refrigeration. We're using gases to remove heat, and via some of these laws that we're going to cover today, you're going to hopefully understand why and how that all plays and works. So the first thing we'll talk about is we'll explain the measurement of volume, define Pascal's law, inches of water column, pressure, that sort of thing. Use Boyle's law, Charles' law, Guy-Lussac's, Dalton's, Avogadro, as I call it, and the combined gas law. Explain saturated vapor, and that's how this applies to cooling. Saturated vapor, that's actually going to be a real important topic. I mean, the gas laws are nice to understand why gases act in the way they do, but really understanding what saturated vapor is, that's going to be the bread and butter, I think, of this chapter. And then explain the three processes that provide cooling effect. So volume is the physical space occupied by a substance. So if we were to just take a balloon, fill it up with water, well, that's your volume, okay? The volume of water inside that balloon. Depending on how much water we put in there is the amount of space. So it can be measured in both liquids and solids. Increases when a substance is heated, decreases when substance cools. You know, like we talked about last chapter, we were talking about the molecules, moving around. We understood that the molecules inside of ice doesn't move around very much. If we're talking about steam, where we have a lot of molecular movement, and therefore we're adding heat to that substance to create those molecules to really move. So a heated gas in a fixed container, the volume increases until the container is filled. Additional heat energy increases pressure and temperature. So if we add heat to that volume of a container, that pressure inside that container is going to increase, or it's going to decrease if we remove heat. We can remove heat by putting it into a refrigerator, putting it into a bucket of ice, whatever the case may be. All right. So pressure, all right, just mentioned that. Pressure, it's the U.S. customary, it's pounds per square inch, or PSI. All right, we're going to see this a lot. We're going to have to know what PSI is, and we're going to have to know how it really affects everything, because everything we measure is going to be in PSI. All right, we've got the international version of pascals or kilopascals. Doesn't matter in this class unless you go overseas, but it is another form of measurement for pressure. All substances exert pressure on surfaces supporting or containing them. So there's always pressure, upwards, downwards, left, right, in between, doesn't matter, there's always pressure. Atmosphere is always exerting pressure on us, all right? We may not feel it, but at sea level, all the air that's surrounding us is pushing down due to that gravitational force. And that gravitational force, keeps everything at bay, and we're roughly about 14.7 psi at sea level. The higher we go up, the less close we are to the center of the Earth, the less gravitational force, and therefore we have less pressure. So just a little quickie here, converting PSI to kilopascals. The other thing too here is we've got PSIA. So PSIA stands for pressure per square inch atmospheric. Okay. We then have PSIG, which is pressure per square inch gauge. So what ends up happening is we've got that 14.7 psi being exerted on us continuously. That's going to affect our gauges. Okay. So what we do is we sort of zero out our gauges. It's sort of like a scale. All right. If I wanted to, let's just say, how much does water weigh? Okay. I'm going to put a container on the scale, and I'm going to pour water into that scale. But my measurement, or my measurement on my scale is going to be off because I didn't zero out the scale. I haven't taken into account what my weight of the container is. All right, so it's the same thing when we're talking about pressure. All right, we have that 14.7. They're rounding it up to roughly 15. We're taking that 15 pounds per square inch and we're calculating that. All right, we're zeroing it out. So that way we're really left with only 90 psi. Okay, and the same applies as our measurement decreases, so does our psi atmospheric. But we're always noticing that there's a 15 psi difference between one and the next. For the sake of our measurements, our class, everything that we do, everything we test is in psi gauge. All right, we just assume we know that there's a 15 psi of atmospheric pressure bearing down on us. That's going to affect things. If you were to go to Colorado, if you were to go somewhere up high in the mountains, that's going to change things. Okay, if you ever notice that your baking directions for, let's just say, baking a pizza at 3,000 feet or higher, or 5,000 feet, you need to bake at a certain time or certain temperature. Why? Because the atmospheric pressure up there is much less. That's going to affect how things cook and so forth. Same thing with boiling. Boiling temperature is going to be much different up at a higher altitude than it would be down below. And we'll cover that here in a little bit and why that is. So we have a formula for calculating the pressure. So we have pressure equals force divided or over area on which the force is acting. So we just have a couple of different diagrams off to the right illustrating how this is calculated. So we have 250 pounds over 10 inch squared, pressure force equals 25 psi. All right, so we're exerting 25 psi with this type of rectangular object. If we were to double, all right, we're increasing the height of this object, but the width is staying the same. We've now got 500 pounds of force being applied to 10 inches squared. We get 50 psi. If we were to take that 250 pound brick and then widen it out, we're not putting as much downward force into a singular point. We're distributing it lengthwise, and therefore we're decreasing the amount of psi that we have. All right, so this point right here is going to have less pressure on it than this point right here. So what we have here is we have a Pascal's law, and basically what it's stating is that as we apply force in a contained cylinder in one direction, we're using this piston, we're going to have an outward direction equal amongst all the different walls of this cylinder. Okay, so whatever the gas is, it doesn't really matter, but we're pushing down 60 psi. We're then going to exhibit force in every single direction at that same pressure level, which is indicated by the 3 pressure gauges here.
Pascal's law states that pressure applied upon a confined fluid is transmitted equally in all directions. For instance, a vapor in a cylinder is a fluid in a confined volume. If a piston were to move and occupy some of that volume, pressure across all parts of that confined volume would increase. If the piston moves outward to occupy less volume, pressure across all parts of the confined space would decrease. A refrigeration system is divided into high and low sides. Think of the high side as one confined volume, and the low side as a separate confined volume. Each side is filled with a fluid, called refrigerant. Throughout one side of a system, pressure is equally distributed as dictated by Pascal's law.
All right, so that's just, getting into the little basics of refrigeration. We've got the high side and low side. We'll definitely cover that in a little bit more detail. But just to give you a little basic illustration of how everything works, okay? We've got refrigerant. It's flowing in this direction, indicated by the arrows. All right, we've got a cold refrigerant. Over here, it absorbs heat, comes to the compressor. The compressor is going to change the pressure. So we've got a low pressure here, we'll just say 60. Over here, we've got 120. And then we're going to come back through here, gets nice and hot, It's going to come back over with that high pressure. We're going to go through a metering device. The pressure is going to drop, and we're going to have cold refrigerant. Okay. Real basic. We'll definitely cover a little bit more of how this really works in detail here in a sec. So the relationship of pressure to volume and heat. As heat is added to a substance, it may increase in volume, it can increase in temperature, it can increase in pressure. If the volume of a gas is decreased, it may increase in pressure, it can increase in temperature. All right, so what we're starting to understand is that there is a direct relationship between temperature and pressure. So if I'm going to increase the temperature in a substance, we can increase its pressure, okay? If we're talking about the volume of a gas, as we start to increase the volume of that gas into, so we're talking about, let's just say a balloon, okay? It's 10 inches round. If we were to increase the size of that balloon, we're taking that small balloon, putting it into a bigger balloon, releasing that gas in the bigger balloon. Well, guess what? I'm not going to have as much pressure, all right, because of the volume. So volume, pressure, temperature, they're all linking together. So compressing gas, heat of compression. So that's energy added to gas by compression. So what's going to happen is we have a piston, all right, or a cylinder compressor that's running. As we start to increase the, as we start to compress this gas, okay, what it's going to end up happening is just by the physical force of the compression between the piston and the valve body or the valve head, you're going to start to generate heat, okay? And so we're going to get just this heat energy that's being absorbed into the gas. So not only are we increasing the pressure of the gas, but we're also increasing the temperature with this mechanical force of this compressor. All right. We also have adiabatic compression, compressing gas without gaining heat from or losing heat to its surroundings. All right. So it's just the two different types of compressions. Effect of pressure on physical state. Pressure affects the temperature at which a substance changes its physical state. Okay, so what that means is that at atmospheric pressure, all right, we're going to boil water at 212 degrees. If I were to lessen the pressure for that water, I'm going to boil that water at a lower pressure. All right, so that means that, and I don't know off the top of my head, but at 14.7 psi, we boil water at 212. If I were to take it down to, let's just say 0, water may boil at 150 degrees. It may boil at 100 degrees. Whatever that boiling point is, there's a boiling point for the water based on pressure, okay? Higher pressure requires higher temperature. Lower pressure requires lower temperature. An example, low pressure in an evaporator allows evaporation of refrigerant at a low temperature. All right, we also have the critical temperature and critical pressure. We'll explain those here in a second. So here's actually a perfect example of this, what I was just talking about, okay? So we've got 212 degrees for the boiling point of water at atmospheric pressure, okay, 14.7. So we're talking roughly 15 psi. So as I stated, you know, we're taking water, we're dropping it down to almost 0. I was close as far as atmospheric pressure goes. Our boiling point for water is actually going to be somewhere around 30, 50, I'm going to say 50 degrees. So at 150, I'm probably at about we'll say 3.5, 4 psi. So the indicator for this is that as my pressure decreases, my boiling point of water also decreases. All right. So if I were to have a perfect vacuum, I can boil water, or not perfect, but just a well, almost perfect vacuum here at 0, no pressure being put on, I'd be boiling at 30 degrees. If I were to go below 0, well then I would start boiling water at negative. And so water would just automatically boil. It would be in a gaseous state all the time. If I were to increase my pressure, and now all of a sudden my pressure starts reaching, 30 psi, my water is not going to boil until it's roughly 250, 270, somewhere around there in that range, 260. So we need to understand that we have this relationship between pressure and boiling point, because this is critical for us when we're talking about refrigerant. All right, we're going to be going from a gaseous state to a liquid state to a gaseous state. We're going to be constantly fluctuating between the two in a refrigeration cycle. So I talked about this a little bit. We have the gauge pressure, which is PSIG. 0 PSIG incorporates the atmospheric pressure, which is 14.7. Absolute pressure, or PSIA, I just say atmospheric pressure that cannot be further reduced. Perfect vacuum, 0 PSIA. Partial vacuum, any pressure below atmospheric pressure. Okay, so we just need to understand the difference between PSIA, PSIG. We're going to be using PSIG, and normally there is no designation when we're looking at our gauges on our equipment. Usually it's just going to tell you that, hey, you know what, it's reading in PSI, and you can just assume that it's PSIG because you're reading it on a gauge. Okay. Units for pressure measurement, we already discussed pounds per square inch. We also have inches of mercury. Inches of mercury are going to be critical when we're talking about things that are less than a PSI, okay? For example, if we're talking about gas pressure, all right, we're working on a furnace, and we need to check the gas pressure inside of there. The natural gas that's flowing inside the piping is actually coming in at a very, very low rate, all right? We don't need a high gas pressure coming into our furnace like we do our water. Our household water pressure is about 50 psi, okay? That's a lot, all right? And everybody's, I'm sure, seen the water hose flowing, and you know what 50 psi really feels like. Imagine that if that were gas. That would just be utterly insane. There's just so much heat energy associated with gas that we don't need such a high pressure. So we're talking about less than 1 inch of psi when we're talking about gas pressure. And since we're dealing with such a small amount, we're actually breaking it down into even a smaller category. And so we're doing inches of mercury, okay? Think of like 1/10 of an inch of psi, or 2/10, all right? So instead of saying 1/10, 2/10, we're gonna talk about inches of mercury, all right? We also have feet or inches of water column, okay? That's also another indicator of, our system, how it's running. Very small, very precise measurement. Tors, bars, that's all going to be stuff that you may run into. That's really stuff associated with like overseas, international units of measurement. I've only seen one piece of equipment that ever ran in bars, and it threw me a loop and had to do all my calculations and conversions, but at that point, Google's your friend. And we also have atmospheres and kilopascals. So what is an inch of mercury, okay? So what ends up happening is we have this cool little device right here, and what ends up happening is as the atmosphere starts to exert pressure on this tub of mercury, what ends up happening is this vial inside here starts to increase, all right? As the pressure starts to decrease, so does my mercury little bubble inside here. This is how we're going to test our barometric pressure, okay? Barometric pressure is a good indicator if we have storms coming in, we have a low front, we have a high front. Depending on the weather condition, our barometric pressure is going to increase or decrease, which is relevant to the atmospheric pressure really pushing down on this mercury. Luckily, we don't use mercury anymore because it's really dangerous and toxic, but back in the day, this is what they had. So we also have this thing called a water manometer, this slinky looking weird thing. Basically what ends up happening is we have this air duct. All right, in this air duct we have air passing through. Air doesn't just travel in a linear motion. Okay, air is going to exert outward pressure along this duct in all these different points all the way around as the air travels through. First we need to have outward pressure, and then air is able to push through. And as it pushes through, it's continuing to push outwards along this duct. Eventually gets to the point here where it gets to the open to the pressure in the duct, this little tube. Well, the pressure is going to want to exert inside this tube. As it exerts pressure inside this tube, it starts to fill the vial, it hits the water. It then pushes the water up or down based on the amount of pressure inside the ductwork, which we then measure in inches of water pressure. Okay, we're also open to the atmosphere. This is critical when we're talking about air duct. We really want to balance the system properly. We can't just put a PSI gauge on there. The PSI, the level is just not enough to really measure our gauge. So we're going to use inches of water column to do that.
So I have a manometer here, nothing too crazy. I've got an open-end tube here, and you can see there's a measuring stick, and I have some fluid filled with water, but originally this was maybe mercury because Torricelli's earliest barometer used mercury. In any case, what I'm going to do is I'm going to take a syringe, and I'm going to attach it to the enclosed tube, and now I'm going to make the space smaller for the same amount of gas that's trapped in this area. So by me making the space, the volume smaller, okay, the pressure is going to increase. So I am going to, Boyle's law, lower the volume by forcing the gas molecules into a smaller space is going to increase the pressure. The manometer is going to measure that increase in pressure. When the pressure was equal, these levels were equal because the pressure in the inside of this tube is equal to the pressure pushing down in this open container. So the force on this liquid level is the same as the force on this liquid's level, and thus you have equal pressure. Now by increasing the pressure, and I'm doing this by making the volume smaller, stuffing the same amount of gases in the same temperature and pressure, and making a smaller volume, I'm increasing the pressure. And what we can do is we can measure the difference, okay, of these liquids to measure the pressure. Right now, if I wanted to measure the pressure, if this was mercury, we would say that I'm supporting, if this is 4, and let's pretend this is approximately 23, okay, so this is 19. So from this point here, I'm measuring 19, okay, millimeters. Okay, now of course I just measured 19 centimeters. So that's 190 millimeters of fluid I'm supporting upward. And I would say that the pressure in this area is higher than the atmospheric pressure pushing down. Right? Manometers use a differential of pressure to measure. So right now, the pressure in this syringe, which is connected, is 190 millimeters of mercury higher than atmospheric pressure, right? There's two forces. There's a force pushing down here and the force pushing down here. Who's winning? Clearly this side is winning by 190 millimeters of mercury, which by the way is a torr. So we would say the pressure in here, if the atmospheric pressure was 760 torr, it'd be 760 plus 190, and that's how we measure the pressure here. Okay, if we go the opposite way, make them equal out again, and now I'm going to lower the pressure by making the volume larger. Whoa, how much higher in pressure is the atmospheric pressure? Well, this pressure is lowered, and this pressure on the open end is winning. Let's pretend it's also 19 centimeters, so let's make that 190 millimeters of mercury. So now the pressure in here is less than atmospheric pressure by 190, So we would do 760 minus, okay, 190, and that would be the pressure here. So this pressure here is lower. Clearly can see the atmospheric pressure is winning by 190 millimeters of mercury, okay? And again, the pressure in here is 760 minus. When we did the other side, we did what? We increased the pressure. We did what? We said, well, this is pushing back on the atmosphere, plus it's supporting the column. So this is equal to the pressure outside, but you have to add 190 to it in this case if we're going to use that. Okay, so manometers are used. You're subtracting. Here we're equal. Here this side is less than the atmospheric pressure pushing down by this much. And here, the gas here is less than the atmospheric pressure by that much. Now, if we don't have mercury, we can change that into water. So, I'm sorry, if this is water and not mercury, we can compare it to mercury's density by height times density equals height times density. Because if you have mercury, okay, mercury is 13.6 times more dense than water. So therefore, its height is going to be 13 times smaller. A heavier volume of water, okay, cylinder being supported. Remember, we're supporting a certain weight, okay? And that weight, for the same amount of weight of mercury, it's going to be a lot less volume. So if this was water and I were to convert it to mercury, okay, I take my, we're going to use 190 millimeters, I divide it by 13.6, and that would be the height in mercury. So if we don't have water, we can certainly get there by doing those differences. So that's all basics of manometers. So I...
All right, so, oh, let me go back there. Just canceled out of there. So anyways, that was just a little bit of a video on the guy explaining how manometers work, the principles behind them and so forth. So you understand a little bit more about, you know, how we're going to really measure using that tool. So we also have compound gauges. All right, these guys are going to be our best friends when we're measuring a refrigerant. All right, they're going to both measure positive pressure and a vacuum. Okay, often includes saturated refrigerant temperature that corresponds to the pressure reading. What the heck does that mean? All right, hopefully you guys can see this. All right, so on our compound gauge, our needle is going to read 0. Okay, as we start to increase and add pressure to our system, all right, now we're talking about measuring the pressure of refrigerant in a refrigeration system. This needle is going to increase based on the pressure being exerted inside from the refrigerant. Okay, so that needle is going to go up and up and up until it finally corresponds to a certain pressure value. All right, let's just say, for instance, we're at 40. Okay, my needles are going to read 40 psi. What does that mean with these other inner guys? So most of our refrigerant, if we're working on residential, is going to be R22. Unless it's a new refrigerant, then it's 410A. The nice thing is we've got this inner chart. So how this corresponds is, if at 40 psi, I'm roughly going to have, and based on the chart, I'm going to guess in between here, I'm going to say 17. All right, I'm going to have 17 on the R22 scale. So the saturation point, or the boiling point for R22, or the saturation I should say, is 17 degrees. So I know at 40 psi my refrigerant is going to be 17 degrees. Okay, if I were to take a jug of R22, or any refrigerant for that matter of fact, if I have no idea what it is and I hook my gauges up to it, just a mystery refrigerant, it could be 404, it could be 134, and I measure my psi, and I measure 50 psi, okay, or I'm sorry, let's go back. I know that it's 70 degrees outside. I don't know what my mystery refrigerant is, but according to, let's just say 134A, I should be reading almost 70 psi. If I hook up my tank and it's 70 degrees and I'm not reading 70 psi, well then I may have something else. All right, I may actually have R22. If I had R22 and I'm reading 70 psi, I should be right around 110. So that's a quick little trick to determine what type of refrigerant that you have in a system. There'll be times where you walk up to a system and your numbers are completely off, okay? And you'd be like, whoa, I thought this was an R22 system. Well, based on the ambient temperature, if the system's been not running, that system acclimates to the outside temperature. So if it's 70 degrees outside, my refrigerant inside is going to be 78 degrees if it's not running or hasn't been running, all right? Once it stabilizes, there'll be a pressure temperature equivalent, and you can find out exactly what refrigerant you have in there. Most of the times, like I said, it's going to be an R22. It may be a 407C, that sort of thing. Now, when we're talking about a vacuum, okay, we have the needle here, and as we start to apply a vacuum to our system, this needle is going to move in the reverse direction. Okay, we're going to go counterclockwise, and eventually we're going to get that needle to drop all the way down to almost 30. Okay, why are we doing that? Well, part of the refrigeration process and prepping the system is that we want to remove moisture. All right, when we went back a few slides, okay, let's see here, to that chart. Here we go. So I have moisture that's in the air, okay? In order for me to boil that moisture out or get rid of it completely, I need to apply so much heat and generate 212 degrees, okay? If I were to have moisture, just water laying around, okay? That's a lot of heat. That's a lot of BTUs. We talked about BTUs a little bit. If I were to decrease my pressure, I'm able to boil that water at a much lower rate, all right, at 30 degrees. So the heat energy involved of boiling 212 versus 30 is drastic, all right? And so what we end up doing is we want to make sure that our system is clear of non-condensables, meaning moisture, different gases, things like that that don't belong in there, things that are just in the atmosphere. And so how do we get rid of them? Well, we start pulling a vacuum on our system. As we pull a vacuum on our system, we start reducing the atmospheric pressure that's being exerted, and we're causing everything to boil at a much lower rate. So we're not even adding any heat or removing any heat. We're just applying a vacuum, and just by physics alone, we're able to cause the water and everything else to boil out. So that's why when we start doing that, we start pulling a vacuum, and that's going to indicate when we're complete. We can't use a compound gauge by itself to know when to pull a vacuum because the measurements are so finite. Just like when we were talking about inches of mercury, we use a thing called microns. Microns are going to really help you pull down a greater amount, just because we have these inches of mercury, and once we hit 30, we just think, oh, okay, we're good. But there can still be a lot of impurities in our system, and really using a micron gauge is going to help make sure that we really pull down to the next level. All right, so what we have here is our percent vacuum. Really, what I'm looking at is, let's just say our PSI, okay? We know PSI atmospheric, what that all means. If I start at, actually, let's go to gauge. Now we'll use, okay, so here it is, 29, all right, inches mercury, that's what we're using, sorry. So at 0, we're equal to 0 microns. So I have a scale from basically 0 to 30. But in that same amount of space, I've got a scale in microns which goes from 0 to 760,000. The difference between 29.92, so we're talking about 4/10, is equal to 10,000 microns. So we're talking about a very small, finite measurement. Why is this critical? Well, it's critical because we're evacuating our systems. We're making sure that there's no moisture. Everything's out of there up to the point where we're really hitting 500 microns, okay? Sometimes 250, depending on how deep of a vacuum we're really pulling. So we want to make sure that all of the moisture, everything else is boiled out. So we're pulling as deep and great of a vacuum as we can. So we're going to hook up a micron gauge, and that micron gauge is going to read off and basically tell us when we're complete. All right, once we hit that 500 mark level, or sometimes even 250. So we have Boyle's law. All right, the volume of a gas varies inversely to the pressure, provided the temperature of a gas remains constant. So in these laws, we always have to have a constant. Okay, if we change that constant, we're going to have a fluctuation. So in this case, the temperature is going to remain constant. So we're going to maintain 68 degrees, and this is what our law states. So if the pressure goes up, the volume decreases. As the pressure goes down, the volume increases. Okay, so we have the Boyle's law basically in a nutshell. So we then have Charles' law. All right, the volume of a gas varies directly to its absolute temperature, provided the pressure of the gas remains constant. All right, so yet again, here's our constant. All right, the pressure is going to remain constant. So as our temperature goes up, the volume goes up. As the temperature goes down, volume goes down. Okay. And then we have Guy-Lussac's law. The absolute pressure of a gas varies directly with its absolute temperature, provided the volume of the gas remains constant. So Guy-Lussac's, hey, we're going to make sure that our volume doesn't change. So pressure and temperature increase, pressure equals temperature increase, pressure decrease equals temperature decrease. Okay. So all three different laws relate to our refrigeration. So now we're going to start talking about our refrigeration cycle. Okay, now we've talked about the three different laws and how they sort of incorporate. So the way our refrigeration cycle works is this. Okay, we'll start off at the metering device. We'll just work in this direction. So coming from the metering device, we're going to have what we call a subcooled liquid. Okay, don't worry about what that definition means, but I'm just going to talk about it until it sticks and you understand the terminology as we move forward through the course. So we've got this cold liquid, all right, that's traveling through our evaporator. The evaporator is going to be the unit that's sits inside your house. It's going to sit either above or below your furnace. And so that refrigerant is going to come through in a liquid state, right? As we start to make our way through the evaporator, warm air gets blown across it. Okay, we've got warm air in the house that's hitting this evaporator. The heat starts to be absorbed into the refrigerant. The refrigerant's flowing through these copper tubes. All right, as the refrigerant flows through the copper tubes, it starts to change. It starts to go from a liquid and it starts to turn into a vapor. All right, we can see that it's a low pressure and a low temperature coming through. Now all of a sudden, we're in a full vapor state, no more liquid. We're going to finally get to the point where we start to call this a superheated vapor, and we're going to reach our compressor. Okay, our compressor is going to, like the name implies, it's going to compress, it's going to squish the refrigerant. The output of that refrigerant now is going to be a high pressure and a high temperature. So we're a high pressure, high temperature gas. We're flowing through outside to the condenser. Once we hit the condenser, we start to release the heat that we've absorbed. As we travel through, we finally get to the point where we're just a hot liquid. The hot liquid comes back. The metering device basically restricts the amount of refrigerant that's able to flow back to the evaporator. By doing so, it's just like a little tiny hole, we'll just say, hits that, and all of a sudden it just sort of flashes, almost entirely, but we have a liquid state still. And by doing so, we go from a gas back to a liquid, and by doing so, we remove all the heat, and now all of a sudden we're back to repeat the whole cooling cycle again. So we can absorb the refrigerant, or absorb the heat, throw it back outside where it gets all nice and hot, and go back in and repeat the process. So that is just refrigeration in a nutshell there. So we have the combined gas law. The combined gas law takes Boyle's law, Charles' law, and Guy-Lucsac's law, combines them all into one, and everything being not a constant, but the ratio among pressure, volume, and temperature of a gas remains constant. And so now all of a sudden we have an equation. All right, if one of these things change, the other one is going to be affected. All right, so we can rearrange this equation to solve for temperature, pressure, or volume.
This demonstration shows what scientists Robert Boyle and Jacques Charles discovered several hundred years ago. Nature's rules of the temperature, pressure, and volume relationships that we commonly take for granted today. Mr. Boyle noticed an inverse relationship between the pressure and the volume of a gas, while Mr. Charles observed a direct relationship between pressure and temperature. As the volume of gas increases, its pressure decreases, as is evidenced when the air is let out of this balloon. The air being released has increased in volume, but the pressure of the air has decreased proportionately. That's called Boyle's law. With a confined gas, there is a direct relationship between pressure and temperature. If the pressure remains constant, the volume increases as the temperature increases. Or if the volume remains constant, the temperature and pressure increase proportionately as well. Notice how the warmer balloon has increased in size, while the cooler balloon has decreased in size. This is called Charles' law. Working together, aspects of Boyle's law and Charles' law explain the ideal law of perfect gases, also known as the combined gas law. This law defines the relationship between pressure, temperature, and volume.
So that was just a cool little demonstration just to show you guys how heat, or the lack of heat, really affects how something operates. Okay, and I say lack of heat because now we're getting to the point where we're removing heat. All right, we have to understand that it's heat removal. We're adding heat, we're removing heat. That's how everything works. Okay, so we also have Avogadro's law: equal volumes of two different gases at equal pressures and temperatures contain equal numbers of molecules, regardless of the mass of the gas. All right, so basically we're talking about two different gases. You can basically add them together and you're going to get a reading. Okay, so Avogadro's law basically adds to the combined gas law to produce the ideal gas law. So the ideal gas law provides a formula for calculating the pressure, temperature, or volume for a known quantity of gas. It's primarily used by engineers rather than technicians. Absolutely right. I mean, we don't have to know the ideal gas law. We're not going to be pulling out our phones trying to figure out, all the equations. In reality, the ideal gas law is used to come up with PT charts. Okay, PT charts are little tools that we use as technicians that are going to tell us what our pressure and temperature relationship is for a refrigerant. So for example, if I have an R22 refrigerant and I want to know what temperature it is at 50 psi, well, I would look on the chart, and the chart will then tell me other refrigerants as well. So every refrigerant is going to have its own PT chart, all right? And the ideal gas law is used to calculate that.
Hey, it's Professor Dave. Let's talk about ideal gases.
He knows a lot about the science stuff. Professor Dave explains.
Let's recall our definition of a gas as the phase of matter where atoms of a substance are in motion and fill their container. If we make a couple simplifying assumptions about gases, we can make some easy predictions. Those are that, 1, particles of a gas are dimensionless points in random motion, and the identity of the gas is irrelevant. It could be anything. and 2, that the particles don't interact apart from elastic collisions, bouncing off one another like balls on a pool table. These things aren't completely true, but they make the math easy and surprisingly accurate, so these kinds of samples are called ideal gases. When examining an ideal gas, we want to be able to discuss 4 variables. 1, pressure. This is the force the gas is exerting on its container, or rather, how much the particles are hitting the sides. 2, temperature. This is the amount of heat energy available to be transferred into kinetic energy of motion. The higher the temperature, the faster the particles move. 3, volume. How big is the container? And 4, moles. How many particles are there in the container? So, how many particles, how big is the container, how fast are the particles moving, and how often do they hit the sides? As it turns out, these variables depend on one another in interesting ways that have been formulated into laws. Let's look at a piston. While keeping the moles and temperature the same, in other words, the same number of particles moving at the same speed, if we compress the volume, the pressure must go up. The particles will be hitting the sides more often because there is less distance to travel to hit a side. That means that pressure and volume are inversely proportional. If one goes down, the other goes up. This is expressed in Boyle's law, P1V1 equals P2V2. If we double one variable, we have to cut the other one in half in order to keep this equation valid. Volume and temperature are also related. If we have gas in a balloon and we heat it up, the particles will move more quickly. In order to keep pressure constant, or hit the sides with the same frequency, the volume will have to expand. This means that volume and temperature are directly proportional. If one doubles, the other must double. This is expressed in Charles' law. When we do calculations with temperature, we must always use an absolute temperature scale called the Kelvin scale. 1 degree Kelvin is the same magnitude as 1 degree Celsius, but 0 Kelvin is absolute zero, the lowest temperature possible, a complete absence of heat energy. This helps us avoid weird mathematical issues that would arise if we were doing a calculation involving a negative or 0 temperature. To get Kelvin from Celsius, just add 273. To go the other way, subtract. The combined gas law is like a combination of Boyle's and Charles'. Avogadro's law says that equal volumes of gases at the same temperature and pressure contain the same number of molecules. Specifically, that 1 mole of ideal gas occupies 22.4 liters at standard temperature and pressure, regardless of the identity of the gas. Lastly, all the variables correlate in one equation called the ideal gas law. This also contains the gas constant R, which makes these calculations intelligible in our man-made units. There are a number of values for R depending on the units, but we will predominantly use this one. This equation is useful when we aren't looking at a change, but just to know the values of all 4 variables at once, like in this case. We could know the pressure, temperature, and volume of a gas, and quickly calculate how many moles of particles must be in the sample. So if you're looking at a sample of gas, and you have 3 of the 4 variables, you can solve for the 4th using the ideal gas law. If you are given some initial conditions as well as some final conditions, you can use one of the other laws to find the other information. Just plug in what you know and solve for what you don't.
All right. It just randomly just ended there. Okay. So hopefully that explained a little bit more in detail of how the gases all work, combine, how the different laws play into effect. Okay. In a mixture of gases, each gas acts as if it were occupying that space alone. So we have the total pressure, so Dalton's law, formula P1, P2 plus whatever equals PT. So the total pressure. So it's the pressure of the first gas plus the pressure of the second gas. All right. Used with PT charts and pressure system measurements to determine if non-condensables are in the system. So how does this really play out? Okay. So if we have a refrigerant, we're looking at our PT chart where our compound gauge is hooked up, and I'm reading, let's just say 70 psi, okay? But my refrigerant, and I know that it's, nothing else is in there, but R22 is supposed to be at 50 psi. Well, there's a 20 psi difference, okay? Why is that? Well, I may have something else that's inside there. It could be another refrigerant. It could be non-condensables. It could be something, entirely, maybe even water in there. And it's giving me a false reading. Why? Because I'm taking the pressure of the two gases, combining them together to create what I'm physically reading. All right, so that's Dalton's law. So just an illustration to show you how it works. So we've got refrigerant molecules in the first class. All right, we're reading a set pressure. We'll just say 50 psi. If we were to test the pressure of a system containing refrigerant and air, somehow it got in there, well, we can see that we're reading maybe 70 or 80 psi. Okay, so P2, P1 versus P2, or plus P2 equals the total pressure of both volumes.
Professor Dave here. Let's talk about Dalton's law.
He knows a lot about the science stuff. Professor Dave explains.
We've learned a lot about ideal gases and some of the laws that describe their behavior. But up until now, we have been examining the relationships between the variables that pertain to an individual sample of gas. But a lot of samples of gas involve mixtures of different substances. So we will want to learn about how these gaseous mixtures behave as well. If we take two different gases and mix them together, will there be any new properties that can be observed? What will be the total pressure? It is the case that as long as these gases do not react with one another, the pressure that each gas exerts in a mixture of gases is specific to the amount of that particular gas that is present. And we will call the pressure of that particular gas its partial pressure. In order to find the total pressure of the vessel, we will simply add up the partial pressures. This is stated in Dalton's law. When you think about it, it makes perfect sense, since pressure is just the force exerted as particles strike the sides of the container. So the pressure from all the particles of one gas plus the pressure from all the particles of another gas should add up to be the total pressure for all the particles, assuming we are treating these as ideal gases where their identities are irrelevant. We can also make statements about the partial pressure of each individual gas as they relate to something called the mole fraction of that gas, which is a measure of the number of moles of a substance compared to the total moles of matter present. And the partial pressure of a gas within a mixture will be equal to the mole fraction of that gas times the total pressure. So if there were 0.25 moles of a particular gas out of 1 mole of total gas particles, that would mean a mole fraction of 0.25. And if the total pressure of the sample was 800 torr, the partial pressure of the gas in question would be 200 torr. Again, this makes sense on the molecular level when we consider individual collisions occurring between the particles and the sides of the container, and the fraction of these collisions that is represented by any individual substance. To see this demonstrated, let's say we capture a sample of Earth's atmosphere at sea level. We know that there will be several different gases in the sample, as the atmosphere is comprised of nitrogen, oxygen, and argon in roughly these quantities, plus trace amounts of a bunch of other things. And the sample as a whole exerts a pressure equal to atmospheric pressure, or 1 atmosphere. But what contribution to this total is provided by each component of the gas? Recall that Dalton's law says that the sum of the partial pressures of the component gases in a mixture will be equal to the total pressure. That means that if we pretend the atmosphere is comprised of only these 3 gases, the partial pressure of nitrogen plus the partial pressure of oxygen plus the partial pressure of argon will add up to atmospheric pressure. But how do we calculate the partial pressure of each gas? Well, again, the partial pressure of a gas is related to the mole fraction of the gas, or the fraction of the mixture that gas represents by number of particles. This means we can take these percentages and divide them by 100 in order to express them as mole fractions. And then we can multiply each mole fraction by the total pressure to get the partial pressure of each substance. So it's quite simple to calculate the partial pressure of each gas in our sample. And we can see that these do add up to a total of 1 atmosphere, just as the individual percentages add up to 100%. We can do trickier calculations as well by including other gas laws. Let's say we have quantities in moles of a few different gases, and we place them into a vessel of known volume and at a known temperature. We could then use the ideal gas law to solve for the total pressure. And then, if we calculate the mole fraction of each gas, we could combine this information to find the partial pressure of each gas. So Dalton's law is quite intuitive when you think about it, but it allows us to do important calculations regarding the partial pressures of individual gases within a mixture.
All right, so definitely a little bit more information and details on how all that really ties together, especially with the ideal gas law and Dalton's law. All right, so now we're understanding vapors. We're starting to understand how everything ties together with the different laws. And here we are at saturated vapor. Okay, so what that is, it's a condition of balance on enclosed quantity of fluid. All right, when a vapor is saturated, often some of the substance is already present in liquid form. All right, usually found where a change of state occurs, such as evaporators and condensers. So what we're talking about is we're talking about a vapor, all right, that's traveling through our refrigeration system, and it's at that point where it can no longer, if it were to receive any more heat or take any heat away, it would potentially change its state, okay? So if we're a saturated vapor and we were to all of a sudden remove some heat, it's going to turn into a liquid, all right? We're at that point again, we add a little bit of heat, it'll turn back into a vapor, okay? So we're fluctuating right on that borderline when we're talking about a saturated vapor, okay? So if heat is added, pressure lowered, more liquid will vaporize. If the heat is removed or pressure increased, more vapor will condense, okay? So think of saturated vapor as basically just that like middle threshold, okay? Any type of heat added, removed, we're going to fluctuate and it's going to want to go one way or the other. Okay, so we have the basic processes that provide the cooling effect. So we have the air exchange. Heat is transferred from warm air to a cooler surface. Okay, we also have a pressure change. Decreasing pressure on a gas causes it to expand and its temperature to drop. And then we have a state change. Solid changing to a liquid or liquid changing to a gas absorbs heat from a surrounding area. All right. So basically, these are just the different ways that we're able to really experience that cooling effect. For us, we're really looking at that air exchange. Heat is transferred to a evaporator. It's a piece of metal that's really cold. That refrigerant absorbs that heat, brings it to the outside. The nice byproduct is of that evaporator when we take when we take a pop can out of the fridge and it's really cold and we take that pop can and we put it onto a hot summer table, it starts to sweat, right? Well, that pop can is starting to absorb that heat, all right, just like that refrigeration system does. So think of that pop can now as that evaporator coil above your furnace, all right? It's just that cold, and we're passing that warm air coming out of that blower motor in your home. It's passing across it, and as soon as that air hits that cold coil, we start to get some condensation forming, all right, where we start to remove that water that's inside our home, giving us that muggy feeling, and we're getting a cool air with it. So not only are we cooling the air, we're also dehumidifying that air as well. So that when we talk about air conditioning systems and dehumidifiers, they work off the same premise. It's just a dehumidifier is geared more towards removing the moisture out of the air as opposed to an air conditioner. Air conditioner is going to remove some of the water, and then we're going to give you also that cooling effect. Okay. And so that's it.